So we're coming to the next part, and in the program, this is officially ligand field theory, but to me, it's kind of the rest of inorganic chemistry compressed into 90 minutes. And I want to give this as a review from, I mean, obviously, as a speaker, we're always giving talks from our own perspective. And so I want to let you know a little bit about my background and where I'm coming from. So for those of you who maybe don't know, I am a bioinorganic chemist, and that's kind of what, besides group theory, initially got me really excited about doing spectroscopy. And so here I'm, very biased. One of my favorite enzymes is on this slide. This is the enzyme nitrogenase that does the remarkable conversion of nitrogen to ammonia using a two-component protein system and multiple cofactors. But of course, it's one of many metalloproteins that are known in bioinorganic chemistry. Roughly a third is the conservative number, and for some, you hear numbers even as much as 50%. But what's fascinating about these cofactors from the perspective of an inorganic chemist is that they're the sites of redox processes, the sites of substrate binding. They enable the unique reactivity. And as valuable as crystal structures are, and these days more and more cryo-EM, this doesn't tell the full story. And so often we want to actually understand not just protein systems, but the catalysts you might be working on, or excited state spectroscopy and photodynamics and all of this in real time on real operating systems. And this is where spectroscopy really provides a route to understanding the changes that occur. And this is a lot of the reason that I am a spectroscopist. And I think I just wanted to briefly show you some of the cofactors that are found in biology, in part because this is a framework for discussing the importance of having a solid background in coordination chemistry. Because I would contend that to understand what is interesting in your system, you have to know what is and isn't normal. And so actually during my PhD, I worked quite a bit on a family of proteins known as blue copper proteins. That's shown here in the upper left. And these are mononuclear copper sites. They look quite simple, but they do something that doesn't normally happen in coordination chemistry. That is that the copper 1 and copper 2 sites minimally distort. And what this is thought to do is to lower the reorganization barrier and to make these proteins much more effective at electron transfer. And so to look at this active site, in one hand, it looks like a simple tetrahedral-ish copper site. But on the other hand, the fact that it undergoes such slight changes between nominally sort of copper 1 and copper 2 sites, that's an important lesson to be learned. And you can only learn that when you have a foundation in coordination chemistry. Similarly, there are remarkable active sites like the manganese 4 calcium site of photosystem 2 that enables photosynthetic water oxidation, or the di-iron site in proteins like methane monooxygenase that do biological methane oxidation. And in both of these cases, we're basically just using the side chain amino acids to build effectively our local coordination complexes. And as we'll discuss later, that means that nature's toolkit dominantly supports transition metals in high spin states. But that doesn't mean it covers all the chemistry that nature needs to do. And that's, I think, the beauty of cases like porphyrins that are found in things like P450, or the remarkable FeMoco cofactor of nitrogenase, where nature really builds the machinery to synthesize more complex cofactors that could not be achieved from amino acid side chains alone. And so for my group and I, this is much of our inspiration, really understanding these unique active sites and not recognizing it simply in biology, but recognizing it in our coordination chemistry and more broadly how these lessons can actually be translated. And so in order to understand how these unique active sites enable different functions, what we do is use a whole suite of spectroscopy here in Mülheim. And so this is, of course, the journey that you're going to be taking this week. Later today, you're going to hear from Maurice about vibrational spectroscopy. So in this part of this has a lot of latency, this pointer, in this part of the electromagnetic spectrum. Tomorrow morning, Frank will move into the UV vis, and I will follow up with the X-ray regime. But of course, spectroscopy generally is just the interaction of radiated matter with your material of interest. We're trying to see how it transforms. And in every limit, of course, we have different spectroscopic selection rules, we have different processes. And so sort of the goal of this school is to synthesize as much information as possible from these different methods. And to do so, it's important that we all share a common language, and that is the language of inorganic chemistry. And so that's what we're reviewing this morning. So we already reviewed group theory, and now what we're going to do this morning is to quickly go through the basics of coordination chemistry, crystal field theory, ligand field theory, which really brings together crystal field theory and molecular orbital theory. Then we're going to come back to the group theory that we had this morning to generate more complex MO diagrams and use those MO diagrams to actually gain intuition, to make predictions about what might be possible and whether or not molecules are reactive. That's the purpose of doing all of this, right? It's not one of those painful exercises that you studied for an exam and forgot about. We really firmly and passionately believe that understanding this helps all of us design better experiments and do better computations as well. And then at the end, we're going to just start a little bit about some of the basic sort of spectroscopy selection rules. And this is really moving from that orbital-based picture that I think many of us are very comfortable with to the state-based picture where spectroscopy really happens. And I think these are important distinctions to make in terms of what you're actually observing versus the model that we as chemists like to use. Okay. Now this first photo is actually one of my very first PhD students, Chris Pollock. He's now a beamline scientist at a large-scale facility in the US. But he always used to tell me that everything he needed to know for grad school, he learned as my teaching assistant at Cornell. And so what we're going to do right now is basically I took my semester's worth of teaching notes from Cornell and I've compressed them into this 90 minutes, inspired by Chris telling me that contained everything he at least needed for his PhD. And so we're going to start with just the basics. Again, many of you know this is just review, so we're all speaking the same language. And that is why coordination complexes actually form, right? We need to at least talk about basic coordination chemistry. And of course, coordination complexes have these sort of general formulas that I'm showing here in the upper left, where we have, typically speaking, our metal that is our positively charged that we can think of as a Lewis acid. And then we often think of our ligand as some type of Lewis base. And these actually form because of the electrostatic attraction of the ligands. And so the formation is due to the stabilization of the ligand orbitals. And as we know well, it's the metal orbitals that are actually destabilized. And in most of the spectroscopic experiments we're talking about, those become the valence orbitals that we're actually probing, right? And again, just a bit more nomenclature on this, of course, we need to think a bit about the nature of our ligand, and we're going to think about the nature of our ligand in more detail later. But just to sort of remember that we talk about things in terms of denticity. We're mostly going to talk about monodentate ligands in most of the examples today, things like the halides or oxides or sulfides, or in this case, pyridine, which also would be a monodentate ligand. But we also have stronger chelators that can be formed by bidentate, tridentate, and tetradentate moieties. And oftentimes what we synthesize as coordination chemists looks quite different than what we have in nature. And so this I already alluded to at the very start of my talk, is that protein-derived ligands, this is to make the biochemists in the room feel happier, right? These are your ligands. They obviously come from the amino acid side chains, and they generally are going to support high spin sites. They're weak field ligands in terms of coordination chemistry, and this is exactly the reason why enzymes like hydrogenase need to use things like CO and CN to actually get the low spin sites that they need to do their reactivity. Now, perhaps an even simpler concept we obviously need to all be on the same page on, and we did this in the first lecture, is that in all of this, we're mainly thinking about what's happening with our 5 d orbitals, right? And we're well aware that in the absence of any ligands, we have 5 energetically degenerate d orbitals that take these general sort of renditions that include our x squared minus y squared along the axes, the z squared along our axial axis, and then within the bisecting planes xz, yz, and xy. And so these are always the orbitals that, as transition metal chemists, should generally be at the forefront of our mind. And what we're always asking is, in more complex geometries, how do these actually interact with the central metal, right? And so what we want to do is to actually build intuition about sort of what happens to my d orbitals, for instance, as I go from a quadratic pyramidal structure to a trigonal bipyramidal structure, and how that differs from the allowed selection rules, for instance, at the octahedral limit. Or if I'm D4H versus TD tetrahedral, how does that actually impact the spectroscopy that I'm actually going to do? And one of the questions I actually was asked more than once during the coffee break was, what happens when my ground state geometry is different than my excited state geometry? And of course, this is something that's way beyond the course of this lecture, but I think this is one of the exciting aspects of spectroscopy, is that we can probe things like excited state distortions and really get insight into how molecules are perturbed not only in the ground state, but in excited states. And one of the things I alluded to already in my group theory talk, and I'm using some enzyme examples here just to sort of invoke this notion, is that in real systems, we rarely have rigorous symmetry. So for instance, this is an example of an iron-sulfur active site in the lower left of rubidoxin. And so it's an iron with 4 cysteine thiolate sulfur donor ligands, and rigorously speaking, the protein itself breaks the rigorous tetrahedral symmetry. But locally speaking, in terms of most spectroscopic selection rules, we can approximate this as tetrahedral. And there is a power in being able to do that, and that power is a predictive power for the intensities and energies of transitions that you will observe. And here are just a few other examples where, again, I'm just invoking this idea of approximate symmetry. This is in a non-heme iron enzyme that goes D3H, roughly speaking, a roughly C4V site, and a very roughly octahedral site. And you can see this is pretty far from octahedral unless I only include the first coordinated atoms. But it's a message I want to sort of bring home to you. One of the things I always, I repeat myself a lot to my group. This becomes a problem with faculty members. But I always think that the best way to make sort of informed insights into your spectroscopy is to start with the geometric structure. Look how much it changes, and start that that's a perturbation, and then the next thing to look at is how that geometric perturbation manifests in the electronic change. And so a lot of times, even if we're not rigorously octahedral, distortions during reactivity or due to redox changes, they're maybe making the molecule more or less octahedral, and these are useful lessons to connect to. Okay, but let's start sort of at the beginning, and the beginning sort of is to talk about crystal field theory. And crystal field theory is really, to me, the theory for physicists, right? Because this is who it came from. It's from Hans Bethe, and his theory is based completely on electrostatics. And so we talked about the fact that, without any interactions, you have 5 energetically degenerate d orbitals. But when I bring in ligands along the z and the xy axis, of course, due to those electrostatic interactions that are stronger along the axes, I raise the x squared minus y squared and dz squared orbitals, while those that actually bisect the axes where the ligands are present form the degenerate set of xy, xz, and yz. And of course, we're mostly inorganic chemists in the room, and these, of course, form the well-known set of T2G and EG orbitals. And a lot of what we're interested in is how our systems deviate from this picture. Now, one of the things I want to point out about crystal field theory is, again, it's purely electrostatic. There's no covalency, there's no direct interaction with the ligands other than just this electrostatic repulsion. And it did actually at least allow us to get some sort of basic insights. For instance, crystal field theory predicted that in titanium-3 hexaqua, which is a D1 system, you should see an optical transition that corresponds to a transition from the T2G. Doesn't want to work with me today, I don't know. From the T2G to the EG set of orbitals. But already what you see is that the optical spectrum is more complex than that. And this is something that Frank will talk to you more about. But in this case, you, of course, can also have a Jahn-Teller splitting that actually occurs, and he'll talk about that more tomorrow. But let's talk about some of the other sort of general sort of failures of crystal field theory and why we needed to go beyond this to really incorporate covalency. And the 10DQ parameters, for starters, were not always correctly predicted by crystal field theory. So for example, crystal field theory actually predicted that ferric hexafluoride should have a larger ligand field splitting than ferricyanide. However, from experiment, it was seen that ferricyanide actually had a much larger ligand field splitting than ferric hexafluoride. Right? So this is the whole process of falsification that Frank was bringing up yesterday. And of course, part of the problem is that the crystal field theory model intrinsically lacks any information about the nature of the ligand and the way it donates. And of course, what we know now is, of course, that cyanide is a sigma donor, as is fluoride. But in contrast, cyanide is a strong pi acceptor. It has empty pi star orbitals on the ligand that can actually accept character from the ligand. And in contrast, of all the halides are actually pi donors. They have ligands in their, or electrons in their pi sets of orbitals that can donate to the iron. And so the important part here is that the nature of the ligand matters. The experiment could not be accounted for by electrostatics alone. And so I think one of the really important experiments that actually showed this was this 1953 paper in Nature, where they actually looked at the EPR spectrum of iridium-4 hexachloride. Okay, so this is iridium. It's going to have a relatively large ligand field splitting. It's D5. So overall, what we get is an S equals 1/2 spin. And what the authors predicted, since iridium has a nuclear spin of 3/2, that it should have 4 lines in the EPR, but actually many more were observed. I'm not showing the spectrum here because in 1953, apparently, you didn't have to put a spectrum in a Nature paper. So they talk about what it looks like, but in fact, it's not in the paper, which is quite interesting. But they do go on to basically say that their much more complex EPR is due to additional hyperfine coupling that's due to the actual 3/2 spin on the chlorine ligands. And so they're kind of detailing of that here, basically saying that they estimate that the electron hole is on a particular chlorine atom for about 3% of the time, and on some chlorine atoms for about 18% of the time. This, I mean, it's kind of an interesting discussion and maybe a bit far from the way we would talk about ligand hyperfine these days. But this was, in some sense, kind of exciting to look at because this was the first time that people kind of realized, hey, it's not just electrostatics. There's a real interaction with these ligands. And in fact, these days, this is something that, for those of you who are familiar with EPR spectroscopy, we see a lot of, right? We see that in something like copper-2 tetraimidazole, which is a D9 system, and due to the nuclear spin on the copper should only have 4 lines. But look at all this rich structure. And that is the nitrogen hyperfine. That is something that we observe and can relate to concepts like covalency. And so the person who really is, I think, credited then with ligand field theory, which really combines the principles laid out in crystal field theory with molecular orbital theory, is Van Vleck. And it relies on symmetry and covalency to form sigma, pi, and delta bonds. And here I just put a quote from Van Vleck's Nobel Prize address. where he said, in 1935, I published a paper in which I amplified and generalized the primitive crystal field theory. Sometimes it makes you not surprised that chemists and physicists don't get along. But he did show that Bethe's grouping of energy levels according to symmetry was still valid, even if one allowed the electrons in the unclosed shells to wander away sometimes from the central ion and take a look at the diamagnetic atoms clustered around it, right? And so this was sort of an early description of covalency and what was happening with that. Okay, so let's take a look first at sort of, again, a concept that I think all of you are very well familiar with, but we just need to be rigorously on the same page here, that we, of course, now don't think just in electrostatics, but we need to actually think about forming bonding and anti-bonding orbitals. And so on the far left, I'm showing a homopolar bond where you have two atoms of the same identity. So their fragments start off at the same energy, and they form both bonding and anti-bonding combinations. Now, we could, of course, also have heteropolar cases, which is closer to what we have in terms of metal-ligand bonds, where the interacting fragments aren't at the same energy, but are actually at different energies, so that when we look at the bonding combination, it is the lower energy, the one to deeper binding energy, that contributes more to the actual bonding fragment and less to the anti-bonding portion, right? And this is just important in terms of thinking about relative energetics of interactions when we think about our MO diagrams. And here, because you will be doing some orbital visualizing with the ORCA code, this is just sort of to remember how these sigma and pi bonding interactions might look and the corresponding anti-bonding interactions. And of course, an important concept that we need to deal with and we'll look at more later is the concept of bond order, which is instructive in our thinking, where we take 1/2 the number of electrons in the bonding orbitals minus the number in the anti-bonding to give us a bond order. And of course, we don't count anything that's in a non-bonding orbital towards bond order, right? And these are, of course, concepts, whether the nature of an orbital is bonding, non-bonding, or anti-bonding, that comes out of the group theory discussion we had already this morning. Okay, so let's start by talking about more complex MO diagrams. So often undergrads generate the MO diagram for water and then everything stops there. And obviously for inorganic transition metal chemists, we need to actually generate more complex MO diagrams. And so I want to start with just some general rules. And this, of course, already comes from the electrostatic arguments that we actually already talked about at the beginning, that our ligand orbitals are going to generally be lower in energy than the metal orbitals that they're actually interacting with. So we would have our filled ligand S and P here on the right side of my diagram, the metal D, and then oftentimes the empty metal S and P to higher energy here on the left side. And the orbitals that are treated in terms of crystal field theory are, of course, these orbitals right here, what we already referred to as our T2G and EG. And so we tend to often be very focused on the sort of crystal field part of this. It's just through bonding, we have some electron density that is transferred from the ligand to the metal, and hence these don't look like naked d orbitals, but rather have contributions of both metal and the ligand. And the extent to which this mixing takes place is how we define covalency, right? In a very ionic limit, the lobes on the ligands are very small, and in a very covalent limit, they become very large, just visually speaking. Okay, so let's just discuss briefly some of the rules we need to generate our MO diagrams, and then we'll proceed to actually use them. So we start by needing to determine the point group of the molecule and to determine how the central atom, so in this case the metal orbitals, actually transform in that point group. And for today we're going to start at octahedral. Then we do the same exercise like we did at the end of the group theory talk to determine how the ligands transform under each operation of the point group to form the symmetry-adapted linear combination of ligand orbitals, or what we generally refer to as sulks, right? And then we allow only the metal and ligand orbitals of the same symmetry to interact in order to form our molecular orbitals. Okay. And so just some general rules for constructing these MO diagrams. The metal ligand orbital mixing is proportional to the overlap of the metal and the ligand. And so that basically means if we have a short metal ligand bond, they're going to interact strongly, and this splitting will actually end up being larger. And metal ligand orbital mixing is inversely proportional to the energy difference of the mixing orbitals. This is exactly the reason why, if you think about carbon, nitrogen, and oxygen as ligands, the interaction is dominantly with their 2p valence and not with the deeper lying 2s. And this is something that clearly comes out of just looking at valence ionization energies from photoemission spectroscopy. I'm just showing here the 3D valence ionization energies for the first transition series, and then for sort of possible interacting atoms. And what you can see is, for instance, if we look at nickel and copper, their 3D valence ionization energies are well matched to that of the nitrogen oxygen 2p, right? And so just looking at these relative valence ionization energies, one can surmise why covalency actually increases as we go across the first transition series, because a lot of this is just energetically how well things can actually mix. This also kind of tells us why the metal 4s and 4p that are energetically to higher energy are going to be less likely to strongly be involved in bonding, right? But it's important to sort of think about this and how it modulates our picture. Okay, so we're back to group theory, and this is why we spent a little bit of time on group theory this morning, just so that these tables are something that you've hopefully gotten a little bit used to looking at. What you can see is that for the octahedral point group, we already discussed, we have 48 symmetry elements. This gives us these 10 actual symmetry classes and 10 irreducible representations. And as we already discussed, I won't go through this again. These are the definitions of all of these symmetry operations. But just to do a quick check, we have A1G, which is our totally symmetric irreducible representation. Important for this discussion are how the d orbitals transform, and so as expected, you can see they transform as T2G and EG irreps, and the p orbitals, so just to sort of account for the 4p and the 4s, these are going to transform as A1G and T1U in octahedral symmetry. And so that at least tells us something easily about how our central metal transforms. That's something you can always just look up on the character table, as long as you're dealing with a mononuclear site. This obviously gets more complex for clusters. And so just like we already did for our manganese hydride pentacyano complex for the vibrational spectroscopy at the end, what we again need to do is to generate the sigma interacting sulks of the 6 ligands, right? And so this is an exercise that we can go through relatively quickly, since we did this before for another complex. But if we look at this, we have 6 ligands, and we have no node along the bond. So you can think of this either as a p orbital pointing directly towards the metal, or analogously, you can just think of the 4s sphere or whatever is easier, because they're going to transform in the same way. There's no node, right? And so we can see then that all 6 of these ligands go into their selves. So for our reducible representation, it has an order of 6 under E. Now, if we do a C3, let me just see, I have that there. That C3 is going to bisect through this axis here. And that means that everything, if I do a 1/3 rotation, 120-degree rotation, everything changes place. So the order under C3 is 0. Then I can do a C2 along this axis, and you can see that everything again changes. If I do a C4, however, along my primary axis, then the equatorial positions all change with that 90-degree rotation, but the 2 axial go into themselves. My reducible representation gets an order of 2. And the same thing happens if I do that C4 twice. I do a 180-degree rotation, but the 2 axial go into themselves. If I do an inversion, that means I pull everything through the middle, everything switches. So it's 0 for my reducible rep. And if I do an S4, that means I rotate by 90 degrees and reflect. Nothing is where it started, and so the reducible rep has a value of 0 there. And then we can do the same thing with a S6 in proper axis of rotation. And so this is back to this question here. We don't have a C6 axis here. We have a C3, so this was our even odd rule, again, coming up in the octahedron for those of you who had questions about this. And then we can do a sigma h. This one is easy to see. Everything in the plane of that horizontal mirror plane goes into itself, so that it has an order of 4 in the reducible rep. And then we do the sigma d that actually bisects between the equatorial atoms and gives us an order of 2, right? So now we have something that we can actually reduce within the octahedral character table. And we won't go through that math again, but we can at least check ourselves. So I can decompose this reducible representation into the irreps using the same formula that we went through in the group theory talk. But by inspection, you can just add up these A1G, T1U, and EG and make sure that I get 6, 0, 0, 2. That has to be a mistake there, because that doesn't add up. Ah, no, it does. Thank you, it does. I'm being diagonally challenged. 4 and 2, we're good. Okay, it's always the wrong time to find a mistake, right? And so we end up with our sigma interacting orbitals transforming as A1G, T1U, and EG. And so what we're ready to do now is to construct an octahedral molecular orbital diagram for ligands that interact only in a sigma type fashion. And so what we do is we have our metal d orbitals. We already looked at our group table for octahedral and said they transform as EG and T2G. I also have the 4s going as A1G and the p orbitals going as T1U. And now I'm going to let them interact with the ligand S and more strongly with the ligand p orbitals to form my bonding and anti-bonding combinations. And here what we see is that the T1U won't have any interaction with the d orbitals, nor will the A1G. They will interact just weakly with these empty metal S and p orbitals. What dominates the bonding are, of course, the 3Ds because of the energetic proximity and overlap. And what we see here then is we only have the EG orbital that can interact with the metal 3Ds. That raises it, makes it anti-bonding, and the T2G actually stays non-bonding. And so then the important question to ask is, does this molecular orbital diagram actually explain our EPR? So let's think about it. We had iridium-4, which is D5. It's a heavier metal, so it's likely to be low spin. We know it's S equals 1/2 from the EPR, so I'm going to put 5 electrons in these orbitals and have an S equals 1/2. And so now my unpaired spin resides in a non-bonding orbital. It has no interaction with the ligand. It doesn't explain my EPR, right? And that means in order to explain my EPR, I need to think about the nature of the ligand. It's back to the same lesson we learned why crystal field theory didn't work. And so we actually have to account for the fact that if we have chlorine ligands, we actually have pi donation, right? And so just to illustrate this graphically, of course, we have electrons in these pi-type orbitals that can also donate into the metal. And this, of course, happens in halides and amides and a range of ligands where you have pi character that can actually donate to the metal. Okay, and so what we need to do is slightly more challenging three-dimensionally, because now instead of having just the orbitals that go along the bond, we actually need to now represent the p orbitals that are going to actually form these vectors that are shown sort of at perpendicular to each other. So these are the actual pi orbitals that I'm just representing with simple arrows. And then what we need to do is, and this is always the task that some people find easier or harder, is to actually then do all of these symmetry operations and come up with the reducible representation. And here, because we have 12 vectors to represent our pi-type interacting orbitals, that one is easy. I have under the identity, I have 12, but then I also have to do every single other operation. I won't go through all of them, but I'll just highlight the C2. So if I do this 180-degree rotation, you see everything in the equatorial plane switches. But for instance, these vectors, if I rotate this 180 degrees, it goes into minus itself, this one goes into minus itself, and I end up with -4 as the character for this reducible representation. Everything else comes out to 0. You can try this during breaks if you want. And then I can reduce that irreducible representation, and you can see that it reduces as T1G, T1U, T2G, and T2U. And so immediately what one sees as the very important part is I now have something of T2G symmetry. I can complete my MO diagram, and what happens, of course, is now this becomes also antibonding, and that means there will be a chlorine character actually in this orbital, and this will be something that in the EPR will have ligand hyperfine. And this just emphasizes the importance of including all of this in our MO-based picture. Okay, so let's just talk briefly about the different types of ligand donors we actually have and their effect on 10DQ. And so on the far left, this is the example that I just showed you, right? We started with the sigma-only donor limit. And so in the sigma-only donor limit, I raise the EG and make it antibonding, but the T2G stays non-bonding. And so in fact, this will have a larger ligand field, but as soon as I can pi donate, this will raise the T2G and the ligand field will actually decrease, right? And then of course we have the other picture where we have pi acceptors, where we have unoccupied ligand pi star. And so now our picture is somewhat inverted because now the metal can actually donate character to the ligand, and the nature of this orbital then actually becomes bonding. It becomes stabilized and bonding relative to where it was here. And that means that the ligand field splitting actually increases when I have an empty pi acceptor on the ligand. Okay. And of course, this is what has led to the well-known establishment of the spectroelectrochemical series. I'm just showing a partial part of this series, but just to sort of remind you that when you look at it, what you always see is that the ligands that can both sigma and pi donate are on the left. In the middle are the sigma-only donors, and then on the far right are ligands that can both sigma donate and pi accept. And this is reflected immediately in the optical spectroscopy that Frank will talk to you about more tomorrow, where you can very nicely see and would predict that vanadium hexachloride with the chlorine, which is a pi donor, has by far the smallest ligand field in the series, and the largest ligand field is when I have the hexacyanide that is a pi acceptor. And of course, the same thing happens if we look at rhodium. But what you clearly see for rhodium, because it's larger and you have more diffuse orbitals, the ligand field splitting generally increases, right? And so these are the other trends that one has. If we have a change in the charge on the metal, right, the ligand field splitting will go up. And this kind of makes sense. The metal is more oxidized, the bonds get shorter, metal ligand covalency increases, and splitting goes up. And then similarly, as I already alluded to, we have trends going from 3D to 4D to 5D metals, where the orbital splitting increases because you have a greater radial extent of the d orbitals, and that results in an increase, right? So we sort of have a general trend on going from left to right in the periodic table that it generally increases the ligand field splitting for a fixed ligand. But as you guys know, it's not so straightforward because we also need to include spin state, right? And so we can, for instance, if we have an octahedral ligand field splitting here, in a D5 configuration, we can have an S equals 5/2 spin, or we can have a low spin, an S equals 1/2 spin. And this is something that you've probably learned when you studied Tanabe-Sagano diagrams during your undergraduate. But what largely promotes high spin complexes is when the ligand field splitting is actually small. So you'd rather promote the electron to a higher energy level, which costs energy. But this energy with a small ligand field splitting is still less than the cost of spin pairing, right? And it's always that trade-off. Do I pay the energy to pair the spins, or do I promote it higher? And of course, if the ligand field splitting gets very large, then promoting this electron here takes too much energy, and so it costs less energy to simply spin pair it. Right? Okay, so what we want to do now, now that we have sort of these basic concepts for constructing ligand field diagrams, we want to actually sort of use this sort of more in real life, and we've kind of already alluded to this, that most of the time when we're dealing with real molecules, they don't have necessarily super high symmetry. And so one of the useful lessons that I've found is to also think about concepts like descent and symmetry, where you start at an octahedral limit, and then you lower symmetry to see how the properties evolve. And we're going to do this just a simple sort of Gedanken experiment to try to just construct a local ligand field splitting for a cobalt pentacyanobromide complex, which if you looked at this based on our previous group theory lecture, you would tell me this has C4V symmetry, right, because of this bromine. But an easy way to construct this without even looking at a character table is just to think about what happens when I lower symmetry. And so intuitively, most of us can start with the octahedral limit and say, look, I have T2G, which with a pi acceptor ligand will be bonding and low in energy. And then I have an EG orbital that'll be actually anti-bonding due to that sigma interaction with the cyanide. And so what I want to do is see first, in order to get to this complex, I'm going to start by just plucking off one cyanide ligand, making it go 5-coordinate, and seeing how the splitting diagram actually evolves. And what you actually see is when I remove a ligand, remember that the pi set is bonding, so it's actually stabilized due to the presence of the cyanide in the z-axis. And so when I actually remove it, it won't affect the xy, that's in plane. But the xz and yz, they'll actually lose that pi acceptor stabilization, and they'll go up in energy. In contrast, when I lose the sigma antibonding interaction, the dz squared should lower. And so this is just a crude estimate of what that diagram would actually look like. And then what I can do is take a next step. So I've moved the 5-coordinate pentacyano over from the previous slide, and now I'm going to put in the sigma donating and pi donating bromine ligand. And so now the way this actually evolves is that bromine will actually have a destabilizing effect in the z direction for both the xz, yz, and the z squared. So the z squared will actually go up, and I will have a 1, 2, 1, 1 splitting pattern, right? And here I'm just sort of drawing kind of a ChemDraw version of what we think these diagrams actually should look like. And what you can nicely see here is the cyanides, right? These are the nice pi interacting pi acceptors, so these are bonding interactions. And in contrast, it's anti-bonding with respect to the bromine. And again, I mean, this is a simple example, but when you have molecules that you're working on and you're wanting to compute, I really encourage you to take the time to think about what is the MO picture I actually expect, right? And it's just very useful, and I think a lot more helpful when you have an idea of what you expect to see. So we went through this already in the group theory lecture. I just want to remind you, again, that when you look at these orbitals, and again, I as a spectroscopist find this super helpful to just be able to assign symmetries by simply looking at orbitals. And so you can kind of easily see that the dz squared, if we think of our z-axis running in this direction, that it is symmetric with respect to the primary axis of rotation. It's also symmetric with respect to a sigma v. So this actually I can immediately assign as A1, whereas if it's asymmetric, remember, that's when it goes as B. And so my dx squared minus y squared becomes B1 for being asymmetric with respect to the the primary C4 axis, and symmetric with respect to the sigma v's that go along the xy axes, and so on. And of course, a doubly degenerate set will transform as E and C4V. And this is just a quick way to sort of, once you know your spectroscopic selection rules, that you can look at the MOs and make some sort of expectations about whether transitions will be allowed or not. I'm not going to go into that because that is something Frank will cover tomorrow, but just to sort of give you a reminder of where this comes from. Okay, the other thing I wanted to comment on is that, again, as Frank likes to remind people of, orbitals are not observables, but they help our thinking, and they are mathematical constructs. So there are many different ways to visualize orbitals in ORCA. And the canonical orbitals that you get out just from a normal print, they often aren't the prettiest to look at, admittedly. And yet they also are the ones that are most closely related often to spectroscopy. But sometimes it's hard to have intuition just looking at the canonical orbitals, especially if you are calculating more complex molecules and the character becomes more and more delocalized. So it's always quite gratifying to look at canonical orbitals for something like ferric tetrachloride. I think that's probably an example you guys have in the excited state practicals, and those will look clean. But in reality, they often don't look clean. And that's why we often use other ways of visualizing orbitals. The localized orbitals are actually quite nice. They display bonds and lone pairs. They'll never show a bond that's sort of not there in a sense. So they're a good set of orbitals, but the spin up and down need to be treated separately, and they don't have well-defined orbital energy. So depending on what you want to compare them to, that could be a problem. For my group, we often like to look at the QROs, the quasi-restricted orbitals that you get from the keyword UNO. These are extracted from the natural orbitals, and for me, they're often in accord with my intuition, and they have well-defined energies, so we can relate them oftentimes more easily to spectroscopy. And then, of course, there's also natural orbitals that can have non-integer occupation numbers that you might get from like a correlated CI type calculation. ORCA does allow you to assign symmetry, and so this is something that sometimes can be helpful in calibrating your thinking. Just to show an example, though, of how one could do this in ORCA, this is an old example now from chemistry from Carl Wieghart's group and calculations done by Frank himself at the time. But this was just a nice example where there was a question of how to describe this nickel complex, whether it was nickel 4 with these diionic ligands, or a nickel 2 where you actually had ligand-based radicals. And so this is just a nice rendition looking at the HOMO and LUMO of this complex, where you can see we have a HOMO that is largely ligand-based, but a LUMO that has significant metal character. And if we kind of like look at this and count the occupied orbitals, we arrive that this is more of a nickel 2 ligand radical description. And this is something quite helpful that one can do in ORCA. But again, one of the things that we want to emphasize is that these aren't calculations that we want to treat in a black box way, right? I mean, there are a lot of things that ORCA can do. And frankly, the fact that ORCA can accurately predict your spectra, to me, isn't that exciting unless you learn something from it, right? And so that's why one really needs to sort of use ORCA as a tool to actually ask questions. And for this, I think one needs a hypothesis-driven approach, right? It's not just put it in a black box and see what comes out. It's trying to ask intelligent questions and have it be an aid to guide your thinking and guide interpretation. Okay, so let's take an example of how we can do this. So what I want to propose is that we're going to use MO and ligand field theory to actually design a catalyst, right? That's in principle the kinds of things we often say we want to do. And so we want to ask the question, how do we make strong metal ligand multiple bonds? How can I weaken the bond to allow for the transfer of an atom? Maybe I want to do OAT and I need to be able to break that bond. And how do simple group theory and molecular orbital and ligand field approaches actually help you decide? Okay. And again, this is something that's been around for a long time. I keep forgetting to put the original reference, but the concept of sort of metal oxo bonding and the concept of an oxo wall, I see people out in the audience nodding. This comes from early work of Harry Gray, first published in 1962, on the vanadilyl ion. But it was something that Harry extended to generally to metal oxos. And here is just a simplified MO diagram where we're just considering in C4V symmetry the metal oxo moiety. So we're dealing just in this case with our filled oxygen 2p's. They're down here, these 6 electrons, and the metal D. So it's a simplified partial MO diagram. But basically what he showed is in this symmetry, the XY will be non-bonding, whereas the XZYZ and the X squared minus Y squared will be anti-bonding. And that means I can afford to put 2 electrons in here, but I will still have a metal oxo triple bond. It will still be a very strong, very non-reactive species. And this is, of course, quite true. We know a lot of crystal structures exist for things like manganese 5 oxos, and they're often pretty dead stable, don't do a whole lot, aren't that reactive, but you can crystallize them. And in fact, you would probably say that by looking at this MO diagram. And what happens is as I start to populate these anti-bonding orbitals, right, as soon as I start putting electrons in these pi star, this bond order starts to go down, right? So for anything beyond D3, I start to occupy anti-bonding orbitals. And at a higher D count, I'm eventually going to have no net bond, right? And so what we do know is that manganese oxo complexes aren't so reactive. But iron oxo complexes, like iron 4 oxo complexes, where D4, we start to populate, we start to see they're more reactive. And that makes sense. That's what I would predict from MO theory, that where these electrons are and how they interact actually matters. And so the question kind of is, Harry, he called this the oxo wall, where the oxo wall basically said that you couldn't make oxos late in the transition series. They just wouldn't happen, right? And it's been a source of some discussion in the literature. There are people who thought that they made, for instance, palladium oxo complexes that would have been an oxo wall violation, according to Harry Gray. But there is this question of, they don't all have to be C4V symmetry. And so this was a nice paper from Ted Betley and Jonas Peters back around 2008. And what they looked at was really how this C4V MO diagram could transform if you had a different symmetry. And so at the time, these weren't complexes that existed. This was really a group theory based paper, basically contending that if you could make C3V complexes where you basically have the C3, the equatorial ligand bent out of plane, so you have the E set actually becoming non-bonding, that you might be able to go to actually much higher D counts because you have more non-bonding orbitals, right? And that was the argument at the time of that paper. About 3 years later, Harry made it very clear that the oxo wall still stands. This was, sort of 50 years after he first showed it. He's always been one to sort of clarify that there are approved oxo wall violations, and that included iridium-7, because if you oxidize it enough, you have low enough D count, that's an approved oxo wall violation. He also, though, pointed out that he had a group member who tried to make it and unsuccessfully. I always feel sorry for that group member, right? It's like it's in there that it didn't work. But the guy's a venture capitalist now, so I think he landed okay, but isn't doing chemistry anymore. It was now actually a few years after that, and I know that Harry Gray actually, this is also a Gray-approved oxo wall violation, because what John Anderson at University of Chicago did manage to synthesize was a cobalt-3 oxo species, where he's using this ligand that, if you look at it, the symmetry in the group theory argument is almost exactly what was in the Betley-Peters paper. And so it was basically about a decade later that vision on pen and paper was realized actually chemically. And he's also an ORCA user. These are ORCA calculations that supported that assignment. But there's been a lot of activity in this area, and there continues to be, in part because people want to be able to synthesize these late transition metal oxo species because we predict they should be so reactive, right? And so these are not just interesting as pen and paper exercises, but they're interesting in terms of what they can enable in catalysis. And other species like these have been invoked, but largely based on spectroscopy. So this was a nice work from Miguel Costas in Spain and Jana Rojtova in the Netherlands, where they identified using sort of mass spec and combined vibrational spectroscopy to identify what they assigned as cobalt-3 oxyl and cobalt-3 oxo species. Okay, good. But now in the last part of the talk, we need to switch gears a little bit and come back to sort of what we're actually seeing in spectroscopy. So we've talked a lot about how we can use molecular orbital theory to actually tune our intuition, but at the end of the day, orbitals are not observables. And I take a lot of, I'm giving credit to Chris Pollack because he found Frank very quotable, and his group meetings always had this old photo of Frank and the bubble with whatever the quote was. So I want to ask your guys' help for like filling more of these bubbles at the end of the week. So feel free to put a write-in on your survey of what could go in a future bubble. I put something in his bubble, but it's too long because he didn't actually say this, but but I think he would agree that they're still useful aids for calibrating our thinking. The problem is, however, we talked about these transition metal oxos. And the reality is when we talk about things like iron 4 oxos, for instance, they don't behave in a neat molecular orbital picture. In fact, one of the things we discuss particularly often with oxochemistry is this concept of two-state reactivity. And so oftentimes these metal oxo complexes in C4V symmetry actually end up having a triplet ground state. And so you pair 2 of the electrons, the other 2 are unpaired, you have an overall S equals 1. However, it's thought that along the reaction coordinate, in order to actually lower the barrier for doing H-atom abstraction, you actually need to cross on to a high-spin manifold. And this is not a picture that I get from simple molecular orbital theory. It is a state-based picture. And it is a picture that when we think about spectroscopy, we need to absolutely remember that spectroscopy involves transitions between states, right? And we can describe this in different ways, but I'm actually going to go back to something from my own PhD. So I did my PhD with Ed Solomon, who's someone who's well known to most physical inorganic chemists. And this was an ancient review article that I did together with Nikolai Leonard, who's now faculty at Michigan, when I was a PhD student and he was a postdoc. But it was basically a review article looking at all the ways over decades Ed's group had studied copper tetrachloride. And he basically has studied the very simple and group theoretically accessible complexes like copper tetrachloride over a range of spectroscopic methods. And he's done this from core spectroscopy to valence spectroscopy to EPR. So basically, in a sense, the summer school that we're doing, Ed did this all initially on copper tetrachloride. The idea basically being that you can take all of these methods together to get a real cohesive picture of electronic structure. And this is, in many ways, exactly what we're trying to do in this school. And we often relate spectroscopy to the MO picture, but this isn't what we're looking at, right? And I think probably with copper, that's all the more tempting to do, because as long as we're at copper 2 and the D9 limit, it does actually map pretty neatly, right? But that breaks down beyond the sort of 1D hole picture. And so in this review article, but generally actually in the textbooks that Ed Solomon has written, he likes to define things between being ground state methods and excited state methods in spectroscopy. And I find that this nomenclature works at least for sort of sorting out major categories of spectroscopy. And so ground state methods, what he means by that is that it's the electronic ground state. And so these are going to be low energy excitations, like the ones that we're often talking about in EPR, for instance. So you're probing transitions that correspond to very small changes in energy, things like the splitting of magnetic orbitals. And the main sort of selection rules that you're concerned about are spin selection rules and transitions between M sub s sublevels. And by the way, Mossbauer also falls into this category because we're looking at small changes of nuclear spin, even though we're probing it with a high energy source. So just to keep that in mind. Now, excited state methods. This is your practical tomorrow afternoon. And this basically covers the rest of the electromagnetic spectrum from fractions of eV to literally over 100,000 electron volts if you're doing hard X-ray spectroscopy. And if we're talking about the near IR and visible, the electrons are excited from, of course, occupied to unoccupied valence states, but you can think of these as transitions between these orbitals, right? That's how we think about it. We're talking about Ligand field or DD transitions, and this, of course, also includes CD and MCD. And, of course, in the visible and UV, we're spanning LMCT and MLCT transitions that we see from absorption, CD and MCD, as well as resonance Raman, and then the core excited states, which encompasses all of X-ray absorption and X-ray emission. Okay, and so what I wanted to do is spend a little bit of time just on this concept of states versus orbitals. So excited state methods involve electrons transitioning from an occupied or semi-occupied or empty MO. And in a chemist's view, this is what we relate to our MO-based picture. And I do think it's helpful to actually do this exercise to sort of draw out your MO diagrams, or at least your ligand field split d orbitals, and go from there to actually explicitly assigning states. And it is, this is one thing that we want you to have a take home is that these orbitals are really not observables. But there are physics papers that literally say that in their title, that they've observed orbitals. And for, you can Google it and you'll find they're even published in journals like Nature. So this is kind of an interesting, it sounds like we're, beating the drum on this, but there are reasons, and you do see this in the literature. In any case, I suspect that most of you were taught UV vis in a state-based picture, right? That's something that most of you have had? Show of hands? Yes? Yes? Okay. Partially. And then, of course, the ground state methods, they involve largely magnetic dipole transitions or between nuclear or electronic spin states. And so in the orbital picture, we remain in the electronic ground state. And I just kind of like to think of it this way, that if I'm doing a ground state spectroscopy in terms of how I draw my MO diagram, right, effectively this ground state term symbol, which I would write as a doublet EG, this is unchanged. For all the excited state spectroscopy, like if I actually am promoting an electron from the T2G to the EG orbital, my term symbol has actually changed. And so my sort of rough grouping is you're doing a so-called ground state method if the many electron term symbol is unchanged, and an excited state method if the many electron term symbol actually is changed. That's the simple grouping that I think of, and it just affects, in some sense, how you use the character tables. I think it's why most EPR spectroscopists rely on them less than, say, those of us doing X-ray or optical spectroscopy, where the connection is a little bit stronger. And keep in mind, the state term symbols are capitalized, orbital labels aren't. So just to try to keep that distinction clean. And so most of the spectroscopy we do can be understood in terms of a few important selection rules. Frank will go through the derivations of these, so this will be presented in far more detail. This is more just as a reminder at this stage. That in excited state methods, we have the delta S equals 0 spin selection rule. We have that, so delta S has to equal 0. This is why we don't see typically spin forbidden transitions. We need some mechanism to impart that. We also have the parity selection rule, which is why D to D transitions, which are G to G, tend to be weak, but G to U or U to G are allowed. This, of course, is not a very strong selection rule. Symmetry breaks the selection rule when you move inversion. And then we have our delta L selection rule, which is the dipole selection rule. And this is one I will use a lot when we do the X-ray spectroscopy tomorrow. This is what makes, for instance, X-ray edge intensities very high, because they are dipole allowed in terms of the orbital angular momentum of the ground and the excited states. And in ground state methods, as I already alluded to, our primary selection rules have to do with delta m sub s or delta m sub I selection rules. And of course, there has been a huge influence of spectroscopy on inorganic chemistry, and this is something that we want to sort of highlight throughout the week. But I just wanted to very briefly go a little bit more through this concept of states and sort of many electron excited states. And so this is just, again, a brief reminder about atomic term symbols and how we actually describe them, where we describe them as a 2s plus 1 L. And L here describes the total angular momentum for the system, and S is the total many electron spin angular momentum. So 2s plus 1 is actually the multiplicity. And so just as a reminder, if we have one electron in these 5d orbitals, this is again at the atomic limit before I've actually brought in a ligand field, then I have 2 times a half plus 1, which gives me my doublet. And then I take my highest value of L here, which is 2, and that gives me my D term. And then in this case, we actually have 5 electrons or 5 halves. 2s plus 1 gives me my sextet. And then I take the sum of these L's, which are 2, 1, 0, minus 1, and minus 2, and that gives me my term symbol S, which is 0. And so what I want to do, of course, is actually, as you guys have actually seen, is to talk in a state-based picture. I don't get to just like draw my nice little MO diagram and only worry about one limit. And this is just sort of a reminder of how complex it already gets when you ask how many ways can I put 2 electrons in 3p orbitals, right? And what I have to consider then is the full range of possibilities of how I can actually put these electrons in. And I've gone through and actually drawn this for you. This is an exercise probably most of you have also done at some point in your undergraduate, but it's more just a reminder of the complexity of the problem that gets even worse for d orbitals. But we end up with 15 possible microstates that we then need to actually assign term symbols to. And so the way that we typically do this is we actually sort of sort them in terms of their m sub L and m sub S values. And we choose the highest m sub S and m sub L for the parent microstate. In this case, that turns out to be L of 1 and S of 1. And we basically then have microstates that span from m sub S of minus 1 to 1 and m sub L of minus 1 to 1. And these are the 9 microstates that I'm showing in red that correspond to a term symbol of triplet P, which is going to be then 9-fold degenerate. And then what I do then is to basically assign all the other possible microstates, and that's basically in the atomic limit where sort of electron repulsion dominates. We basically have the highest spin term symbol will actually be lowest, and then the highest angular momentum will follow when 2 states have the same total spin, right? And so this actually is, for many of you who recall Tanabe-Sugano diagrams, this is in fact how we construct the left side of a Tanabe-Sugano diagram, right? This is a diagram where the many electron states are ordered by electron-electron repulsion, okay? And so we just did the P2 example. I'm not actually going to do the D2 example other than to tell you there is a formula for calculating how many states you actually have. And so it's 2 times the number of orbitals factorial divided by 2 times the number of orbitals minus number of electrons factorial, number of electrons factorial. So if you plug this in, for 2 electrons in 5d orbitals, you end up with 10 factorial over 8 factorial, 2 factorial, or 45 microstates. And this is basically what we've sorted here, where we see for D2, our highest S and L is the triplet F, and then this is basically ordered on the left-hand side. And this is, of course, a relatively easy example where basically we move from the atomic limit where electron repulsion dominates to the ligand field limit where the the ligand field splitting actually dominates. And so we change from atomic term symbols to the actual term symbols we would get from molecular orbital theory, right? And that's the difference between the left and the right. And in the D2 case, of course, at least for octahedral ligand field diagrams, we actually always stay high spin. But of course, we do have the fact that we can actually end up at a strong enough ligand field for higher D counts actually having a transition between the high spin weak field limit and the low spin ground state limit, right? And so the strength of the ligand field is actually increasing in this direction relative to electron-electron repulsion. And then at some point, we effectively cross over. We go from high spin to low spin. And so just to show this graphically, this is a D6 Tanabe-Sagano diagram, right? And so we start with our quintet D, but in a ligand field, that will actually split, and that will give me my quintet T2, and then my lowest lying actually quintet E. And basically, what you can see here is that I have a possible transition that would go from this quintet T2 ground state to move one of these electrons up here and give rise to the quintet E, right? And so how strong the ligand field is basically just is increasing the relative energy of that quintet E state, right? And what you'll notice is this is a spin allowed transition, right? And everything else higher is spin forbidden. And you can kind of see that this is then actually costing higher energy. And this is something that you very clearly see if you look at the Tanabe-Sagano diagram, not just in the D6 limit, but in the D5 limit. When I go to the D5 limit, I have a 5/2 system. So I have a sextet ground state, and I have one electron in each of the d orbitals. It's completely symmetric. It gives me an A1 term symbol. That's the sextet A1. But what you'll notice is that everything here is much higher in energy. And that's basically because all of these transitions are spin forbidden transitions, and I have to pay the energy cost of actually spin pairing to form even the lowest lying quartet state. But importantly, in both of these, you see that this is the point where we cross over from high spin to the low spin manifold when the ligand field is actually strong enough. Maybe just some other comments about this. These spin forbidden transitions are, in general, quite challenging to see, but they are observed for things like manganese 2 hexaqua, so this is a D5. And just like you saw in the previous Tanabe-Sagano diagram, these actually are all spin forbidden transitions. But what's quite interesting is that what you do see is that they differ in width, and a lot of that can actually have to do with the nature of the de-excitation and how much excited state distortion you have. So some of you had questions about things like that. That is something that one can assess through various types of spectroscopy, like for instance in resonance Raman and in time-dependent Heller theory, that you can start to assess these kinds of differences. But here I do want to point out, you do see the delta S of 1 transitions. These are all quartet transitions, but you don't see any sextet to doublet. So seeing these delta S of 2 transitions is very challenging, and this is something that for me as a spectroscopist also inspires me. I think it's always interesting to think about what are the experiments you can't easily do? What are the things you predict by theory could exist but you've never seen? And this is something I won't talk about in my X-ray spectroscopy talk because it's a bit more advanced, but it relates closely to ligand field theory. This is work from 2 of my previous group members, Ben van Kuiken, who's now an instrument scientist at the European XFEL, and Anselm Hahn, who is at ThyssenKrupp. And what they did was some of our early work using 2-dimensional X-ray spectroscopy, where you take a 2p6 3dn ground state, you do a dipole allowed transition to a 2p5 3dn plus 1 intermediate state, and then you let that decay to a 2p6 3dn prime state. And if you look at the difference between the ground state and the excited state, if these two are the same exact configuration, in physics speak, we say there's 0 energy transfer, or it went back elastically to the ground state. But if these two are different, it actually turns out it's a DD transition, that actually comes on this axis. And what we see is if we take a cut of this Rix plane, we can start to map out the DD transitions. And because of a little trick that there's 2p spin orbit in the intermediate state, we start to see spin-forbidden transitions quite easily in this method. And so here I just want to take a moment to relate some of these funny concepts that you learn in undergrad to something that impacts the science we actually really do in my group. And this is just to show you that for something as simple as ferric hexachloride, the inelastic line in our Rix, that's the zero energy transfer line, is that sextet state here. And every feature we see on the energy transfer is by definition spin forbidden. That is the case that this Tanabe-Sagano diagram shows, and also what you would work out. And these are the features we actually see. And then we can go to, say, the ferrous complex, and we can also see the spin allowed quintet to quintet, and we can map out above that all the spin forbidden transitions. So these are just the kinds of things that for the whole Mülheim team, I think gets us kind of excited is what is sort of the next experiment that you could maybe do that really builds off these basic concepts that we're trying to highlight and teach this week. And so with that, I'm just going to sort of close by just reminding you that in all of this that we want you to use molecular orbital theory and ligand field theory as a tool, but not forget that you're dealing with transitions between states. We've been through these selection rules just briefly, especially for excited state methods. Frank's going to go through that in detail tomorrow. And for the ground state methods, Alexander Schnegg will go through this in detail in the EPR talk. And Dan will do that in the Mossbauer talk. So if this all went by too quickly, don't worry. These are all things that are going to come up again with all of the speakers. But we just wanted to make sure you sort of had a general overview of it. And with that, I want to thank you guys for your attention and thank Frank, MIT Open Course, and Otterbein for any slides or images that I may have borrowed. And yeah, I'm happy to answer any questions.